Hi, I'm Larry Dignan with ZDNet, and we're here with Honeywell's Tony Utley and Patty Lee, and we're going to talk about some quantum computing developments they have going on, and also giving it some real-world use cases. Hi, folks. Thanks for joining me.
Happy to be here. Pleasure.
So I guess, Tony, kick us off with you're launching your first generation of your quantum computing with quantum computer, which made a decent splash a few months ago. Walk me through what's happening.
Sure, I'd love to. Yeah, so back in March, we had talked about that Honeywell was going to be releasing, the world's highest performing quantum computer within 3 months, and 3 months later, we were able to do that. So for the last about 6 months, we've been working with folks on our system model H0. What we're talking about today is actually the next generation of quantum computer. So as of this Thursday, we will have launched our system model H1. And the important thing about what we've done right now is really two things. First, we are working with 8 different enterprise companies in industries that are both related to what Honeywell does as a core part of our business, from oil and gas to chemicals and materials to logistics, as well as areas that are close adjacencies that we have just started to tap into from a quantum computing standpoint, like financial services and automotive. And the second big thing is we have strategically designed our H1 generation of system to be upgraded over time. So it starts its life as the most capable quantum computer on the planet, and 2 weeks later it's even more capable, and a month after that it's even more capable. I liken it to if you use a service like Netflix, imagine next week it was twice as good, and a month after that it was 10 times as good, and 3 months after that it was 1,000 times as good. That's what we've been able to do with our H1 generation of quantum computer.
And Patty, what are some of the challenges in terms of making quantum computing, available for real world use?
Sure. So the hardware, it's always a big challenge. Most of our system, it's all about control. Our qubits are given to us by nature, so every atom, every ion is perfect, but then we have to control the environment so that we remove a lot of the noise, a lot of the instability, and sort of, all the things in the environment that could affect our qubits. And so that's a big challenge, is getting our hardware to be very precise and very stable, very robust, environmentally, and in all of our lasers and electronics control.
And it also requires very cold temperatures, correct?
That's right. We used liquid helium. That's very cold temperature. But those things are actually rather robust these days. We can design it so that the system maintains the temperature quite steadily. And so it's, in some ways, it's actually a little easier than controlling the room temperature to get it that cold and keep it sort of within a, millikelvin of the temperature we set it to.
Yeah, the interesting thing about this approach is trapped ion, including our own version of trapped ion, can work at room temperature. We choose not to. And the reason we choose not to is because when you do cryogenically cool it to kind of the 4 to 10 Kelvin range that we do, you get much higher kind of pressure stability in your ultra high vacuum system, which leads to longer lifetimes, which leads to some very important characteristics of quantum computing, which is how long can you maintain coherence of this quantum information in these qubits. And that really provides some additional capability to our customers.
So for an enterprise, you're not really going to have one of these systems necessarily sitting in your data center. It's almost all going to be available by the cloud primarily, correct?
That's correct. Yeah, especially right now, these systems, and the way we have done it is by strategically making it more capable every time we do an upgrade for it, which may be, you know, next week, it may be next month. It's changing so dynamically that the one thing we can assure folks who ask to buy a physical system from us is by the time we get it set up, we will already have a system that is more capable, and it might be thousands of times more capable. So we've done something pretty novel here, which is we have a subscription model for the utilization of our system. And we've done that just for the things I suggested earlier, which is if you're a subscriber, you get the benefit of this system constantly being improved over time.
So do you wind up paying by qubit or project, or I guess what's the subscription look like? What are the parameters around it?
Yeah, think about it like a streaming service. You get access over the course of a month. You basically pay for an amount of access that you're going to get. And then we dedicate time to your sessions. So our customers are able to come in and have a significant amount of time, you know, on something on the order of 8 to 16 hours where they're able to focus on the kinds of use cases that they really care about. And it really, at this point in quantum computing, takes that kind of effort to be able to make significant progress. It's not I can run it for 2 minutes and have something, you know, so spectacular that I go and write a paper. This is hours of work, both in terms of fine tuning the algorithms, but also because many times there's interaction between our quantum computer and some classical computer. And our customers are doing hybridization of algorithms to be able to utilize both simultaneously.
So Patty, what are the challenges with cultivating, you know, software developers for this?
Yeah, so programming a quantum computer is very different because the interesting algorithms are really using the properties of quantum mechanics. And so general, you know, programmers of a classical computer may not be familiar with that. So, you know, right now there are these quantum programmers that are somewhere between a mathematician and a physicist and some computer science background that really understand both the programming side and the computers and the quantum theory to be able to make use of the power of quantum computing. And I think we're also working with a lot of universities and organizations to sort of educate the next generation, computer scientists to really learn quantum programming. And I think that's going to be really important going forward as these systems become more available.
So do you think programmers are going to have to learn a lot of like physical sciences and mathematics and algorithms? I'm just trying to figure out where, you know, you're going to get these folks, because they're going to have to be polymaths to some degree.
Yeah, so the nice thing about it is they don't have to know like atomic physics, they don't have to understand the hardware, but they do need to understand quantum information theory and sort of the basis of quantum programming, how to construct circuits, and things like that. That would be really helpful. But, you know, we've kind of removed it so that, you know, the programmers don't have to deal with the hardware as sort of before, when it's more of at the research lab level, you kind of have to understand the whole system end to end.
So Tony, walk me through some of the use cases you're seeing so far.
Yeah, there are 3 areas that are showing the most promise right now, and that is optimization, machine learning, and chemistry. And kind of materials and chemistry tend to fall into the same kind of category. And what we're doing with a quantum computer, and that's oftentimes one of the things that people ask, is in a problem that's an optimization problem. Let's say you want to figure out if you have planes that are going between airports and there is a storm that has come in and disrupted, how do you optimize where those planes end up with those passengers so that you can minimize, you know, the total travel time, you can minimize the impact to passengers. Just adding a few planes and a few airports, that starts to, increase in complexity very, very fast. So what quantum computers are doing are each qubit, each quantum bit is being mapped to some variable that is a binary variable, meaning it is, think of it as hot or cold, on or off. And as you have those variables, the more you add, the more complex that problem becomes for classical computers. And so what we're doing right now with our customers is taking a problem like that aircraft routing problem, shrinking it down to a size that we can run on our quantum computer today, knowing full well that with each additional qubit you add, you're doubling the capacity to be able to extend that problem.
Okay, so it's really what quantum does well is it basically handles a lot of variables better.
Yes, the more variables into a particular problem, the more complex it gets for a classical computer, and the better you have that ability to then map it to a quantum computer. The other one that shows a lot of promise right now is this idea of chemistry. You know, these are quantum systems, and so mapping a quantum system like a molecule to a quantum computer allows you to think of it basically the way that molecule would interact. So you can imagine variables as you're trying to design a new molecule, and you're saying, what kind of dopant, what impact would I have on this molecule if I put in a dopant, or if I changed the lattice spacing of the parts of the molecule, or if I did a different pressure. Those are all things that have a quantum outcome to that particular molecule and can much better be mapped to these future quantum computers. So it's very exciting. These are times where we're purposefully shrinking down problems so that we can prove that they work out today, knowing full well that as you quickly increase these capabilities of the quantum computers, you can massively add harder and harder problems.
So Patty, what industries have you most excited about quantum computing?
I think in the area of optimization, that impacts a lot of different industries, like, you know, for example, routing and even financial sectors, you know, logistics companies, and you know, and they can apply, you know, optimization and machine learning algorithms with their quantum computer to their existing system. And so that could start to have some impact. Also, I think in terms of materials, we're starting to be able to simulate some interesting material properties, even with a few qubits. And I think there are a lot of advancements that are ongoing that could reduce the number of resources that's needed, so that, you know, before we think we need a lot more qubits, and now we can accomplish the same thing with fewer qubits, especially with our mid-circuit measurement and qubit reuse feature on our system that's unique to our system. And so I think even material and condensed matter science, that's going to have a near-term impact.
And then Tony, you guys are working with a lot of different partners, and the one that caught my eye was Accenture. Do you see a day where, you know, systems integrators will be on the quantum computing bandwagon like they are ERP or some of those traditional areas?
Absolutely. Yeah, to me, it's nearly inevitable that there's going to be a quantum cloud. And as you think about quantum cloud, this is multiple kinds of applications that are tapping into using quantum resources. And at that point, maybe just a little bit, right? So something like a quantum processing unit, a QPU, and you as a customer may never know which part of your job got sent to a quantum computer versus a GPU versus a classical computer, but it's all being done behind the scenes. And for some of those very sophisticated, complex interactions, we're going to have system integration that has to happen with how do you put that into your own business development cycle. In fact, that's some of what we're doing right now is doing that advanced planning to say, we know where this quantum computer exists right now in terms of its ability to tackle the use case that you're working on. We also can plot out, as we increase the capability, as we increase the size of the quantum computer, how quickly that looks like it's going to hit a part of your business cycle that's going to make a big impact. And so we're already thinking about those planning steps that say, where are you going to insert this into your development process? How are you going to adapt your infrastructure to be able to accept this in? You know, is this going to be I need one answer once a month, or is this going to be something that's more of a continuous operation? Because that presents very different kinds of challenges. So I absolutely see this integration effort that's going to be a big part of quantum computing.
And as far as roadmap goes, you know, when do you think we'll see this like truly commercialized?
See, we are commercializing it right now, and I know you probably mean, when are you going to see it kind of ubiquitous everywhere? I think we're still going to have somewhere between 18 and 24 months till you have an even larger swath of enterprises that are utilizing quantum computing. Because we do see customers that are still standing back, or they ask a question that says, well, how much is this going to save me today? And when I hear that when I hear that question, the first thought is there's some education that still needs to happen right now, because the era that we're in, that everyone is in, is about building trust. This is where we are very fortunately in a position that you can run on our quantum computer and get a quantum answer, and you can also run a classical simulator and say, am I getting the answer I expected to get? And that trust building is extremely important, because we are going to very quickly cross that threshold where there will not be an ability to fact check that answer using classical resources. And if you haven't taken this time to build that trust, you know, imagine patient data, imagine your most sensitive intellectual property data, imagine financial services client data. I mean, these are things that you want to know are being treated most securely, and knowing that you can trust the outcome of that answer.
So Patty, if we're, you know, 18 to 24 months away from, you know, a broader adoption, what's the talent pool look like? Can we handle that now, or we have to start recruiting a lot of quantum developers?
Yeah, I think it's a good time to start recruiting quantum developers, because they're actually pretty hard to find them these days, and so we both need to grow that pool, that skill set, and also and so I think the companies that are actually investing now get a huge advantage, because this is a pretty contested, pretty short supplied pool at the moment.
We're also seeing some pretty interesting things happen with our partners in the ecosystem. And I'll take a company like Zapata Computing that has both the capability to do this algorithm development and use case work with end customers, but they've taken an opportunity to abstract back a layer with their Orchestra software, so that you don't have to have a quantum computing degree or be a quantum theorist to be able to utilize a quantum computer's workflow. Similarly, our partners like Cambridge Quantum Computing, with their human software, which is focused on quantum chemistry, you can be a chemist as opposed to a quantum chemist to be able to use those abstraction layers of software. That's going to be really important for adoption. Being able to make sure that the users of quantum computers can think about their own specific domain, but don't have to be experts of how any particular quantum computer works.
Okay, so in short, we'll have to build a bunch of bridges to traditional programming to quantum, basically, from multiple disciplines?
Absolutely. And we're going to want to see that. We're going to have folks whose job it is um, scientists, chemists, analysts who do optimization, material scientists. All of these folks are going to have very real use cases where they're going to be wanting to use quantum computers without having to learn the intricacies of how do you program ours so that our atoms do the things that they're doing. So it's going to be necessary to learn why quantum computers do what they do. But as long as you can abstract it back a layer so that they can be topic area experts, subject matter experts in their own subject, but not necessarily quantum computing, that's when you'll see that adoption curve really start to take off.
Okay, thanks for joining us. Interesting stuff.
Pleasure. Thanks for letting us be here.